Randomization. What is randomization? SystemVerilog lets you create the random values for variables to test all the possible conditions in your design, not just the ones you think of. This this is especially helpful in constraint random testing. Reasons why you might prefer random values instead of fixed test cases when verifying a chip. The randomization is essential in verification because it allows us automatically generate a wide variety of input scenarios which helps improve coverage. Unlike the fixed test vectors that may only cover expected sequential cases, randomization can cover corner cases and accept ex- unaccepted behaviors. By using constraint randomization, we can still ensure the generated values are meaningful within the legal or interesting range, while maximizing the number of different paths and state exercised in design. This makes our test bench more powerful and efficient. We can also use functional coverage to measure what we exercised and guide the randomization to cover untested cases. Use repro- reproducible seeds lets us debug the failure even though the values are random. Rand versus RandC. Rand generates random values. RandC generates the random cyclic values. It goes through all possible values without repeating until it has to. RandC ensures that all possible values are generated without repeating until the full cycle completed, which is ideal for small data type where we want exhaustive exhaustive coverage. For example, if we have a 2-bit variable, ranc will goes through all four values 0, 0, 1, 1, 0, 1, 1 before repeating any. This is useful when we want to guarantee that every possible value is tested. On the other hand, rand may repeat values and skip other entries, which is fine when we are more concerned with the random distribution than completeness. Next topic is a constraints. You can guide the randomization using constraint, so the values are still random, but within the limits. Let's do an example. Um, let's see one example. We zoom. So this is one of the example of packet. So in this example, I define the address and use a constraint where address is greater than 5 and at less than 200. So by calling the this class in my test bench as a packet.pkt and in initial block pkt equal to new, and then repeat the repeat the loop 10 times pkt.randomize. Using this command, this code, the it will randomize different values of different packets, and then I write a dollar display to display the address. So using this code, we can generate the generate different address, and all address are in between 5 to 200. If we change the value, let's do, so instead of 5 to 200, between let's do between 10 to 20. And let's run the code again. So as you can see, I run the code, and so as I did the constraint between 10 to 20, the address values are limited to 10 to 20, between 10 to 20, and greater than 10 and less than 20. Uh, let's do instead of rand, we can use, if I use a rand c. Let's see if it is doing all 10 scenarios or repeat from 11 to 19. So it should it should give us between 11 to give us the value between 11 to, if I run the code using, okay, using control A. So yeah, we are getting 17, 19, 11, 15, 10, 16, 13, 12, 14, and 17 again. So it so these are the values the address generated by randomization and rand c, and Yeah. So, so basically, the constraints, the question arises that why does question arises that what happen if you don't put any constraint in random variable? What is the difference? Why do you want to put a constraint? What is the reason behind putting a constraint? So basically, we can say that by using constraint, we if we don't apply a constraint or randomization in system verilog, we will generate a values across entire limit. So as we can see that if I put the constraint between 5 to 200, it generate only the value between 5 to 200. But if there are if I didn't put any constraint, then it will generate the values across entirely entire legal range. Like the legal range for bit 7 down to 0 is maybe 0 to 255. So it will limit that. It will not cross that the address, but still it will be entire limit use entire limit, which might include values that are invalid or unrealistic for for our specific design. Constraint allows us to restrict the values to a specific range or pattern, which help us avoid illegal test cases and focus our test on meaningful scenarios. For example, in network packet, we might want avoid addresses values received for control. Constraint can also help us steer the randomization of a new or untested cases, improve our overall coverage. Okay. Next topic is line constraint and randomize. So you can call randomize round bracket on an object and even pass the and you can even pass the constraint at that time. So let's see on one example for this. So here in the class packet, we already seen this example. If we write packet.randomize, it will it will give the random value. But if we write a packet.randomize with address 128, so here if we do this, then it will specifically, if I run the program, it will specifically gives 128 value. and if I give 10, then it will specifically give 10, and if I give 2 228, it gives me the warning that, and then it gives the 10 address equal to 10 again. Because why this happened? Because our constraint is address should be greater than 5 and less than 200. So 228 doesn't match this constraint. Let's see if I change the constraint. I remove this 200 constraint. Let's see if 228 passes. Now, yes. So as you can see here, yeah, here is the last value 228. Even the initial values goes above 200 because we remove that constraint, but still, yeah, still we got to 228. So so by inline constraints we can pass the values of the packets or values of the data by using a randomize for randomize the object. And why might let's think, why might you use a inline constraint instead of defining it in the class? So the answer is inline constraints are useful when we want to control the randomized value for a specific test case without permanently changing the default constraint class's default constraints. So class's default constraint will be remain there, and then we want to uh, randomize a specific value test case without, so we can use the inline constraint. For example, if normally randomized packet address between 0 to 255, but one test I want to force to 128. That's if you just write randomize, you might miss the 128, but you specifically want the 128 address to be tested, then you can use an inline constraint with randomize with curly bracket address equal to 128 semicolon curly at bracket ends. This allows temporary the test specific control over the value without affecting other tests. So at that time you can, the test value will go to 120, address will be 128, and it will test that value, and then it continues the remaining values. Introduction to Constraint Random Testing. As our chip design gets bigger, it is harder to write enough manual tests to check every part. Direct test only checks what we already known might go wrong. But the constraint random testing or CRT helps us to find surprise surprise bugs by using random input controlled by constraints, so the inputs are still realistic. Setting up CRT takes more work because we also need a way to predict the correct result. But once it is ready, we can run hundreds of tests without checking them by hand. That saves a lot of time. CRT also use seed like starting number to create different tests each time. This makes one CRT test as useful as many direct ones. Later will learn about about how to check what part of the design were really tested using functional coverage. Let's see in detail what is randomization. When people think about random testing, they often randomize only data field, fields using $random. But this doesn't find many bugs, just simple data issues. Most bugs can come from complex control logic, so we need to randomize every decision point that might change the behavior of the system. That includes configuration setting, environmental variable, delay, errors, not just input data, raw input data. Device configuration. One reason bugs are missed is most tests assume the design stays in a known state, but real system changes dynamically. For instance, a time division switch had many channels turning on and off constantly. Initially, the engineer used manual test script and missed important cases. Later, using CRT, they randomized the configuration of each channel and looped through it. This approach tests much more much more this approach tested much more in real world behavior. Environmental configuration. It is not enough to test just the device. You need to test whole environment it interact with. One company tested PCI Express switch by randomizing number of buses, number of devices and settings like master and slave roles. This lets them explore many configurations automatically, something that would be very hard with the fixed test. Encapsulation input data. Sometimes input data is wrapped up within the many layers like TCS TCP message inside an IP packet inside the Ethernet. Each layer has its own setting and all can be randomized. You will need constraint to keep them valid. For example, correct checksum or length. But also flexible enough to mm, allow allow testing with injected error or protocol violation. Protocol exemption and error. Protocol exemption and errors. In real system, error will happen. It's just matter of time. So one of the hardest and most important job in verification is checking how your design responds when things go wrong. Can it handle a drop message? What what if a CRC check fails? A good testbench doesn't just test normal behavior, it must also inject random errors at the random time and make sure the system handles them safely without crashing. These are often the bugs you only find with careful randomized error injection. Delays. Delays are a part of every communication protocol. A signal might comes 1 to 3 cycles later, or data might show up anytime between cycle 4 and 10. But many testbenches just use the shortest delay to run faster. That can hide bugs. Instead use random legal delay in every test to explore the full range. Also, some designs are sensitive to clock jitter, tiny shift in timing. By sliding clock edge slightly, you can detect bug that would not show up otherwise. Just remember you are checking for functional issues here, not violating the timing rules. Those are for static timing tools. Primary input data. This this is the kind of randomization most people started with. Input data like a bus transaction or ATM cell. It is pretty easy if you if your transaction classes are structured well. Just remember real data often goes through many protocol layers and you may want to include errors that adds complexity and value to your test.